Hey everyone, I am Miss Hu, your physics teacher. In this video lesson, we're going to go through electromagnetic induction. This is a topic in both the SPM and IGCSE physics syllabus. If you'd like to know more, please feel free to do your own research or you can watch my other educational videos. What I'll be covering in this video lesson are just the general information you would need in order to answer your questions in the examinations. Now, before you start on this topic, I would highly recommend that you get to know the topic on forces on a current carrying conductor, as well as Fleming's left-hand rule, to make sure that you can understand this topic. So if you haven't learned that or you don't fully understand that yet, please watch my videos on that topic. And also do watch DC motors if you can. If you already know that foundation, then you can start. So, first of all, let's have a general understanding of electromagnetism. So, as you should already have known by now, electricity can generate magnetic fields. So, just to show you the pattern here, yes, electricity can actually generate magnetism. And the reverse is also true. Magnetism can also generate electricity. Now, I am not saying that it is a reversible process. That's not what I mean. What I mean is that this process can go both ways. Electricity can generate magnetic fields, and magnetic fields can also generate electricity. And that is, in a nutshell, the concept of electromagnetism. So, electromagnetism includes both electricity and magnetic fields working together and observing how the interaction is. That means what's a product of this interaction. So, based on what you have learned about forces on a current carrying conductor, we know that current placed in a magnetic field can produce a force, like in this diagram, which I have taken from my slides on this topic. So if you have magnetic fields produced by permanent magnets like this, and you have a current carrying conductor, that means a current flowing through a wire placed within this magnetic field, the combination of these two would produce a force. So what you'll find is that you can also produce current instead by applying a force within a magnetic field. And that's what this video lesson is about. Now, what is electromagnetic induction? What a mouthful, right? The term electromagnetic induction here refers to the production of an electromotive force, short form is EMF, okay, across an electrical conductor in a changing magnetic field. So again, electromagnetic induction is the production of an electromotive force across an electrical conductor in a changing magnetic field. So if you're not sure what electromotive force is, you need to recall what you have learned in electricity. So electromotive force, you can think of it as a fancy term that means voltage. Electromotive force is quite simply the voltage of a power supply. Now, some textbooks or some literature might write current. It's more correct to say electromotive force, but generally when there's an electromotive force, current will also be produced. So electromagnetic induction is producing not only an electromotive force or voltage, but also current. Scientific definition though, please use the term electromotive force instead of current. So that's why I have that written over here. So electromagnetic induction is the production of an electromotive force across an electrical conductor in a changing magnetic field. In your syllabus, you have to learn that there are two methods of electromagnetic induction. We can move the wire across a magnetic field, or we can move a magnet bar towards or away from a solenoid. So if we look again at the concept that I've written here in general, super general, okay? So force applied across a magnetic field. That means we apply a force on a conductor across a magnetic field, or we can apply a force of the magnetic field across the conductor. Combination of the force and magnetic fields will produce current. So what we'll be going into, of course, is these two methods in more detail. Now, in both cases, there must be movement. So if they were both stationary, nothing's going to happen. This is related to energy conversion because what happens is when you move something, there's kinetic energy. This kinetic energy will be converted to electrical energy. Makes sense, right? So if there's no movement, there's no electrical energy generated. So there has to be some movement. So what we're going to go into next is these two methods in more detail. And we're going to start first with moving a wire across a magnetic field. Now, say for example, like in this diagram, we have two permanent magnets placed at a distance from each other. And because there's space in between, there's going to be magnetic fields generated. And the magnetic fields always flow from north to south. So let's say these green lines, which I'm drawing here, represent the magnetic fields generated by this permanent magnet. Now let's say this yellow bar here represents a metal conductor. So that means current can flow through it. Now at the moment, there's no current flow because it's not part of a circuit. But once we move the wire across a magnetic field, that could generate current. Now remember that for this to work, the wire needs to cut across the magnetic field. So if they're moving in line, parallel, there's no current generated. Now, if they're moving parallel to the magnetic fields, then that's not going to work. The wire needs to cut across the magnetic fields. That means if say these are magnetic fields and this is the wire, it needs to cut. So it can either cut downwards or cut upwards. So if you're moving parallel, like slicing, then it doesn't work. Some of you will ask, what if you're cutting at an angle? So instead of cutting straight across, you cut at a diagonal. Can this also work? Actually, yes, it can. There will, of course, be a difference in terms of the magnitude of the electromotive force or current induced. The value is the greatest when it's perpendicular. When you cut at an angle, then the value is a little bit less. The magnitude of the electromotive force or current induced will depend on the angle of the cut with the magnetic field. So at 90 degrees, it's actually the greatest angle. Any other angle will be less than 90 degrees. So the smaller the angle, the lower the magnitude of the current or the electromotive force. When it's parallel, it's zero. So that's why there is no electromotive force or current induced. So again, you must remember there must be movement because kinetic energy converts to electrical energy. Now, if you can recall what you've learned about forces on a current carrying conductor, you had to determine the direction of the force induced, right? And you had to use Fleming's left-hand rule. So Fleming's left-hand rule, you have to have your thumb, index finger, and middle finger all at 90 degrees to one another. Let me get it in frame. And let me make this larger. Okay. So remember, you need to have your gun and trigger finger. So all must be 90 degrees. Now remember, force, magnet, current. So the mnemonic that I have come up with, and you can choose to use this if you want to, or you can use another one that works better for you. But the one that I've come up with is feed my cat. Feed my cat. Feed, F, force, my, M, magnet, cat, C, current. Feed my cat. So when you wanted to determine the direction of the force induced, you had to line up the magnetic field and current directions using your index and middle finger first to determine the direction of the force induced. But this is to determine the direction of the force induced. In this case, though, we are inducing electromotive force or current. Now, let's focus on current in this case. We want to determine the direction of the current. Now, because current is being induced here, force and magnetic fields are the one that are inducing current. You cannot expect to use the same hand rule because different things are being induced in this case. Different things are being generated. Different things are being produced. So you cannot expect to use Fleming's left-hand rule. This is where John Ambrose Fleming found we had to come up with another rule. In this case, Fleming's, you got it, Fleming's right hand rule. Yes, you've got two rules. Okay. Just to let you know, if you're confused between these two rules, I will have another video where I will compare both Fleming's left hand and right hand rule in general to help you clear up any confusion. But for now, let's focus on Fleming's right hand rule. So to use Fleming's right hand rule, you have to have the same thing, your thumb, index finger, and your middle finger all at 90 degrees. Now, again, remember, gun and trigger finger, all 90 degrees to one another. What each of these represent is exactly the same as with Fleming's left-hand rule. So you will still have force, magnet, current. Feed my cat. So I'm going to write that here. In fact, I'm going to move this a little bit more to the side. So here we have, whoops, force, magnet. In this case, magnet meaning magnetic field because it's a magnetic field between north and south. And this would be current. Again, FMC, right? Feed my cat. So if any of you have cats at home, this would, of course, be a little bit easier for you to remember. Okay, feed my cat. If you have your own method, like I said, please feel free to use that method that works better for you. Now, how do we use Fleming's right-hand rule? So we're going to backtrack to this diagram. So what you need to do is you need to line up the information that you have and then use your hand to find out the direction which you are looking for. So we have the magnetic fields from north to south here, and we need to know the direction in which this wire is moving across the magnetic field. So let's say we have this wire, say, moving it upwards. So I'm going to draw an arrow upwards to indicate the direction of the force being applied. Now, some books and some literature might say motion because you're moving the wire instead. I'm using the term force here because I'd like to create some cohesion between Fleming's left and right hand rule. I don't want you to get confused. Oh, why are they all called different names? So let's call it the same name. So it's force. We apply the force onto the wire this time. So have your hand line up. So remember, we've got the magnetic field, so pointing from north to south. So I'm going to follow the diagram here. So north to south, and the force is going upwards. So you find that the middle finger, the current, is now pointing towards you. You do need to use some imagination here to visualize this in 3D this time. So it's going towards you, right? Let's label, let's label this wire here for a bit more clarity in the explanation. Let's call this HP and then this HQ. So when you look at it in 3D, P is closer towards you, Q is further away. Well, the other way, P is closer towards you, Q is further this way, from your perspective, right? So when you have your hand lined up, okay, okay, make sure that your right hand is following my right hand and look at the diagram. So you have north to south, going from right to left. Your thumb is pointing up and your fingers pointing towards you. That means in this perspective, current is flowing from Q to P. That's right. So current is flowing, induced is flowing from Q to P. So that's generally how you use Fleming's right hand rule. Another example, let's say in this case, let's have the wire moving down this time. And you can see that the magnetic field is going from north to south, which from your perspective is from left to right. So you want to determine now the direction of the current flow. So I'm going to label the edges again. Let's call this X and Y. And we want to determine, is the current flowing from X to Y or from Y to X? So have the fingers line up with the information that you have. So you know that magnetic field is going from north to south towards the right. So you got to get your index finger to point to the right. Now, don't change the fingers. You need to rotate the hand. So keeping north to south, you can see now your thumb's pointing upwards. But according to this diagram, force is moving downwards, which means that you have to get your thumb to point downwards while maintaining the magnetic field from left to right. And you can see now that the middle finger is pointing towards you, just like before. That means from your perspective, the current is flowing towards you. Because X is nearer you, that means current is flowing from Y to X. So I'm going to label that here. Current is flowing from Y to X. That's how you can use Fleming's right-hand rule to determine the direction of the current. I'm just going to label the force here just to get a more complete diagram. Let's look at one more example. I'll move my face here and put it right here so that you can see the hand in place this time. So now we've got a magnetic field like this. So it's not left to right or right to left. North is at the bottom, south is on top. So which means the magnetic field is now flowing upwards from north to south. Let's say the wire is being moved inwards. That means away from you. So again, you've got to use a little bit of imagination to apply the 3D, diagram motions here and all that. So right hand rule. Now, magnetic field is going upwards, north to south. The force is away from you, away from you. So now you can see, okay, north to south, thumb is pointing away from you, following the diagram is going into the paper. You can see that current is flowing towards the right. So that's the direction of the current that has been induced inside the wire. That's how you use Fleming's right-hand rule. Now, let's look at the second method. So now why there is a second method is because normally when electromagnets are involved, there will be a solenoid involved as well. So if you recall, a solenoid is an electromagnetic coil. It is when we take a wire and we loop it into a coil and we make use of this coil for electromagnetic purposes. So a wire coil like this that is used in electromagnets is known as a solenoid. Now, when it comes to solenoids, there will be electromotive force or current induced. But to determine the direction of the current, you can't use Fleming's right-hand rule because it's a coil. Where is it going to point to, right? There's nowhere to point to. So a little bit weird, doesn't apply in this case. So that's why we're going to learn of other methods in this situation. In this case, we will use a magnet bar that we push in and out the solenoid. Why? Because a bar magnet like this has magnetic fields around it. And remember, we want the wire to cut across the magnetic fields. So when we move the bar magnet, you can see as you move the bar magnet through the solenoid, the wires on the solenoid will cut across the magnetic fields. And that is sufficient to induce current as well as electromotive force. So that's the other method. But because we can't use Fleming's right-hand rule, we have to learn of another method to determine the direction of the current flow inside the coil. But first of all, just to point out to you, inside this coil we have a galvanometer. So if you don't know what a galvanometer is something like an ammeter, except that the center is in the zero. So that's why it's sometimes called a zero center galvanometer. So the zero center galvanometer is used in this case because the galvanometer can show us the changes in direction in the circuit. So the needle can deflect to the right or can deflect to the left. Unlike a typical ammeter or voltmeter, where the needle can only deflect to the right. Like this. So as you can see, the typical voltmeter and ammeter has zero on one side, and they will only deflect to the right. If you connected the voltmeter or ammeter incorrectly in the circuit, you might find the needle goes behind zero instead. But you can't see the value because there's no scale behind. So this is where we can use a galvanometer to determine the direction of the current flow as well as the value. So you can think of a galvanometer as being something like an ammeter, but it can show us both directions. A galvanometer is usually extremely sensitive, so it's not something that we normally use in a circuit to measure high values of current. But in this case, we can use a galvanometer because the current induced is usually really small, so it's enough to just see the value in terms of is it a large deflection or a small deflection. A larger deflection means greater current, smaller deflection means less current, and we can also see the changes in directions. So the symbol for a galvanometer is usually just a circle with the letter G inside, or you might sometimes see the symbol being drawn, something like this, a scale with the needle in the center. So these are the typical symbols for a galvanometer. You can look at this as being something like this. So you've got the scale here and the needle pointing to the zero that's in the center. And yes, sometimes they have the zero in the center here just to show you, yeah, zero is in the center. Before we go to the direction, first of all, let's learn Faraday's law. So Faraday's law states that the magnitude of induced EMF or current is directly proportional to the rate of change of magnetic flux. Wow, what a mouthful, right? What does that all mean? Basically, you can think of it as Faraday's law explains the relationship between the magnitude of the induced EMF or current with the changes that are happening in the solenoid over here. So when they say rate of change of magnetic flux, the term magnetic flux here refers to the shape and the area of the magnetic fields that are around the magnet bar. So when you move the bar magnet, you've got the magnetic fields around here. But what happens is when the wires cut across the magnetic fields, there will be some changes made to the shapes of the magnetic field, or in other terms, a change in the magnetic flux. So when the change of magnetic flux happens at a greater rate, the magnitude of the induced EMF or current will also be higher. Makes sense, right? Because if there's a greater change, there's going to be more current that's being induced. Duh, right? Logic, common sense. So based on this, we can just come up with a quick list to explain the factors that affect. So based on this understanding now, it is very easy then to determine what are the factors that affect the magnitude of the induced EMF or current in the solenoid. So what we are looking for is basically what can increase or decrease the rate of change of the magnetic flux. So obviously it has to be speed, right? But I'm going to write here relative speed of motion because it's not just how fast you move the bar magnet, it is the relative speed. So relative speed doesn't refer to only just moving the bar magnet. So let's say this is a bar magnet and this is the solenoid. You could move the bar magnet in and out, or you could move the solenoid, or you could move both. If you're moving both together, they're both moving, but there will be no EMF or current induced in this case because they're not cutting. So that's why we don't just say speed. Relative speed, that means relative to one another, the bar magnet to the coil. So when you do this, the relative speed is zero because they're moving together. So it's got to be one moving, one stationary, or both could be moving towards each other, but not together. Another one would also be the number of loops on the coil. Because the more loops you have, the greater the rate of change, right? Like if you have, for example, one with less loops and one with more loops, obviously, when you move the bar magnet, Okay, the magnetic fields are going to cut less when there's less loops and cut more when there are more loops. So a greater rate of change of the magnetic flux. So rate of change doesn't mean speed only. It refers to within that period of time, how much change of the magnetic flux is there. So more loops in that same period of time that you're moving with the same speed, there will be a higher rate of change. Now remember to say it's number of loops, or you can say number of turns actually. Don't say number of coils. There is only one coil here. Many loops or many turns. One coil. There are two coils here. Another factor would be strength of the magnetic field. Because if the magnetic field around the bar magnet is greater, there will be more magnetic field lines. So for example, if the one on the left is not as strong, there'll be less magnetic field lines. If it's stronger, there'll be more magnetic field lines. So I want you to imagine that if, let's say, we were moving these bar magnets, so if we were moving two bar magnets with different magnetic field strengths, like this one, there's less magnetic field lines compared to the ones with more magnetic field lines, then more magnetic fields are being cut at the same time, correct? So that's why the strength of the magnetic field also plays a role. I'm just going to put this one side here. Yeah. So the more magnetic fields that they have, that means the greater the rate of change of the magnetic flux in that same amount of time. Another factor, and this is not commonly discussed, but logically, I know some of you would already have thought of this, even the cross-section area or the diameter of the wire would play a role, because if the cross-section area of these wire, you've got one smaller one bigger one, when you have, let's say, the same magnetic field being cut across the larger or smaller one, the larger one, there's more space, right? There's a greater diameter, more space for the electrons to move, therefore more current can travel at the same time compared to the smaller diameter. So a larger area also increases that rate of change of the magnetic flux, therefore inducing more EMF or current. Now, there's just one more factor you need to know, which is the presence of the soft iron core, and why the soft iron core can change the induced EMF or current is because soft iron, if you recall what you've learned about magnetism, is an excellent temporary magnet, right? It easily magnetizes as well as demagnetize, which means that if you have a soft iron core in the solenoid, like so, when you bring the bar magnet nearby, the soft iron core will be magnetized because of the presence of the magnetic fields. And that increases the magnetic fields that exist, creating a greater rate of change of magnetic flux as we move the bar magnet in and out. So that's why a soft iron can also increase the induced EMF or current. Without it, not so much. Now, you might come across other factors as well. Some of them could be secondary factors, meaning that they don't directly cause the rate of change of magnetic flux, but it changes something, that changes something else, that changes the rate of change of magnetic flux. Those are what we call secondary or tertiary factors. Usually for your exam, we prefer to focus on the primary factors, which means these are the factors that directly affect the rate of change of magnetic flux. So focus on just these few for now. Okay, I'm just going to put this into a nice little list here. There we go. And now, to determine the direction of the induced current. To do this, we will refer to Lenz's law. Lenz's law states that the direction of an induced current is always such as to oppose the change in the circuit or the magnetic field that produces it. And again, I know you're looking at this and you're like, whoosh, I don't know what was just said and I don't know what I'm reading here. Actually, it's a lot easier than you think. The key word here that you need to focus on is the word oppose. The direction of the current will always oppose the changes that produces it. We're going to look at that on the next slide, but before we get into that, let us first re-examine the right hand grip rule. You should have learned this under the concept of magnetic fields around a coil. So a quick look over here. Let's say we've got the solenoid like this, and you can see that there is current flowing inside this solenoid. So let's say the arrows here represent the direction of the current. So using your right hand, remember, physics is the best. So show me the best sign, right? Now look at your hand and see, which part of the hand resembles a solenoid? The fingers, right? So your fingers are going to represent the solenoid, in this case, the direction of the current flowing in the solenoid. So as you can see in this diagram, the current in the solenoid is flowing upwards. So we need to get our fingers to also point upwards. So you can see it point upwards. Now, where your thumb is, that's where north is. So you can see your thumb is pointing to your left, which means that the north pole on the solenoid is on the left side. That's how we use the right hand grip rule. We're going to make use of this right hand grip rule to help us determine the direction of the current being induced in the solenoid. So what we have on this slide here are 4 different diagrams, and we're going to see how the solenoid responds to the movement of the bar magnets. Let's say in the first diagram, the bar magnet is moving towards the solenoid. Now, remember that the solenoid is not your friend. Whatever you do, it is going to try to oppose it. So the best way to fight against an incoming magnet is to try to repel it. So how does the solenoid repel the bar magnet? It's going to create a south pole on this end to try to repel the incoming south. So if this side is south, that means the other side has to be north. So I've got the solenoid drawn in such a way with the coil wrapped around a soft iron core just for a bit more clarity in terms of the direction. So how do we determine the direction of the current? We're going to use right hand grip rule. So have your thumb point towards where north should be, which in this case is to the right. Let me just put it side by side so you can see pointing to the right. So your fingers, as you can see, should be moving downwards. That means that the direction of the current flow on the solenoid is downwards, like this. What if the bar magnet was being moved away? Now, remember that opposing doesn't mean repel. Opposing just means it fights whatever you're doing. So if you're pulling away, it's going to try to pull back. How to pull back? It's going to attract. So this side is now going to be north and the other side is going to be south. You can think of the solenoid as being a petulant little child. It's like this child is like, okay, I'm not going to make it easy. You give, I don't want. I don't want. You take it away. Then you take it away. No, 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 I want. Give it back. So it's fussy, it's petty, and it's very, whatever you do, it's not good enough. You give, it doesn't want. You take it, it wants it back. Yes, that's how the solenoid is like, all right? So in this case now, the north is on the other side. So you can see your fingers are now going upwards, which means that the current flowing on the coil is upwards like this. So opposite direction to the one before. You should be getting the hang of this now, right? So let's look at this diagram. So now let's say we flip it. So the north pole is now moving towards the solenoid. Remember, it's going to oppose. So it's going to repel. So if it repels, this side is now north and this side is south. So again, using your right hand grip rule, so north is on that side, fingers are pointing up. So the current in the coil is also moving up. And if the bar magnet was being pulled away, remember, oppose just means it fights again. Doesn't mean repel. A lot of students always think, oh, if oppose means repel. No. So if you pull away, it fights. Fight how? It will attract it back. So if it tries to attract it back, that means now this is going to be south to try to attract that north pole back in. So this side is north. So pointing towards where north should be, fingers are now going down. That's why current is also moving down like this. And that's how you can use Lenz's law with the right-hand grid rule to determine the direction of the current flow inside the solenoid. So just a quick note before we move on, I'd like to talk a little bit about the galvanometer. We already know that a galvanometer needle can deflect to the right or to the left. A lot of students make the wrong assumption that the galvanometer needle will deflect according to the direction of the current flow. So they thought that, for example, in the first diagram, because the current is flowing to the left, they think that the galvanometer needle will be deflecting to the left, and at the bottom to the right, here to the right, and then here to the left. Now, that's not true. So I'm just going to undo that. So the misconception here happens because a lot of books teach it that way. They say, oh, if the current's flowing to the left, let me just draw it separately here. They tell you that the needle is going to deflect to the left. Now, the reality is that the direction in which the needle deflects, whether it's to the left or to the right, it doesn't depend on, oh, current flowing left and right. No, it depends on how the construction of the galvanometer is, because a galvanometer inside is a wire coil also with some magnets in there. So if you had coiled it differently or placed the magnets differently, then some galvanometers may deflect to the right, although in the diagram it shows it's going to the left. So don't think, oh, it has to deflect to the left or to the right following the diagram that shows us the direction of the current. No, sometimes it could be the opposite. It could even show you deflecting to the right and to the left like this. Is it wrong? No. It depends on how the galvanometer was, constructed to begin with. So when you see the galvanometer needle in this kind of questions, in these diagrams, you just need to compare the different diagrams. That means you need to see, okay, this diagram goes to the right. This diagram goes to the left. What does this tell us? We compare, because of the difference in direction of deflection, this means the current is flowing in opposite directions. And if we find in certain cases, maybe the deflection of the needle may be greater, let's say like this or like this, that means same direction, something like this, that means same direction, but the one with less deflection, smaller current, while the one with a greater deflection, bigger current. So that's what the galvanometer is used in these kind of diagrams. It's just to tell us the direction of the current and to compare the magnitude of the current flow. Doesn't tell us, oh, left, right, all that. Not a factor in this case. And that's it for this video lesson. So if you found this video educational and helpful, please click like and subscribe for more lessons, solutions, and exam strategies from your physics teacher, Miss Ho. Happy studying!